It's a story of ambition, rivalry, and philosophy. A time when mathematicians weren't just solving equations, they were trying to rebuild the very foundations of truth. Welcome back to another episode of Breaking Math. I'm your host, Autumn Fanav. And today we're diving into one of the most fascinating and surprisingly emotional chapters in the history of ideas, the Great Math War. Our guest is science writer Jason Socrates Bardi, author of The Great Math War, a sweeping narrative that takes us from the rise of logicism and formalism to levels of infinity and beyond. We'll explore what happens when human ego, politics, and world events collide with pure mathematics, and why the questions asked a century ago still shape the age of artificial intelligence today. So, Jason, what first drew you to the story? Was it history, philosophy, or something personal that made you want to write The Great Math War?
Yeah, that's a great question. It was actually all of the above, and it really started in a very personal way because I was at my dad's retirement party in 2017. He was a professor at Penn State, and he was retiring. I was telling one of my father's colleagues about my first book, The Calculus Wars, the famous fight between Newton and Leibniz over who invented calculus. And she said, "Oh, that reminds me a lot of David Hilbert and this dispute that he was involved in, known as the foundational crisis in the 1920s." And I had never heard of it, and so I was interested. And then she told me, well, nobody's ever really written about this before. And of course, as a writer, those are the golden words, ding, ding, ding. In my mind, an alarm bell went off. And then so I started researching it. I started working on it slowly at first, just getting some articles and reading them. And about 2 years later, I was working on my proposal, and I was very serious at this point. This is what I'm going to write my book about. So I was having a conversation with my father over the phone, and this was in the very early days of the COVID pandemic. And I told him what I was working on, and I told him one of the main characters was Bertrand Russell. And he said, "Oh, we almost named you Bertrand Russell." And I just was floored by that because I had no idea. They did name me Socrates, and in my introduction, I talk a little bit about that history of the names. But it was apparently one of these things. Bertrand Russell was one of my dad's heroes at the time. He was an anti-war activist during the Vietnam War. And I actually stopped my dad in his tracks because I told him that the Bertrand Russell I was writing about, the Bertrand Russell of 1900, not of 1970, when I was born, when he died. He actually died 5 days after I was born. But in 1900, 70 years earlier, he was a very different person. He was a mathematician. He was a philosopher, of course, but he was also pro-British. So that was the personal aspect. And it got even more personal when my father died a few weeks after that conversation during the pandemic. And really, that was one of the last conversations I ever had with him. And I was very influenced by that because, of course, in this book, there are a bunch of the characters. Bertrand Russell lost his father at an early age. His girlfriend, Adeline Morel, lost her father at an early age. George Cantor, one of the main figures in the book, he lost his father. He also lost his son. So there was this kind of grief all over the book, and it was extremely hard for me to deal with this in the writing of the book. I had such a personal feeling for this kind of loss because of the loss of my own father. So I wound up making it, very personal in a way. I wasn't talking about my own experience, but I was using my own experience to talk about, for instance, what it was like for George Cantor or what it was like for Bertrand Russell to have lost their father and what that means. And then, the other thing you were asking about is mathematically. So once I started researching this and I, started looking into set theory and, teaching myself set theory and, studying infinity and the different types of infinity, what I call big infinity and small infinity. And your listeners, of course, will correct me, denumerable and non-denumerable infinity. It's funny to read comments and reviews because, of course, writing about math, there's a lot for a general audience. There are a lot of people out there who will approach a book like this with trepidation. I'm not a math person. Will I understand it? And, they'll appreciate aspects of it, many aspects, but, often that person will say, well, it was good. There's a little too much math in the book. And then, of course, the person who has a technical math or engineering background who really, really wants the mathematics, their comment will be, there's not enough math in this book. So how do you please both audiences? That's always a challenge.
Now, why does that metaphor of the philosophical clash between those three categories, logicism, formalism, and intuitionism as a war, fit?
Right. So for a couple different reasons, and I am, of course, aware of the fact that some people complain about using war metaphors for academic disputes. I mean, there is that idea out there that you shouldn't call something a war, the war on drugs or any other type of war. War should be reserved for actual wars. However, in this case, the main characters used war metaphors all the time and fighting each other and, characterizing the other person. L.E.J. Brower, who was one of the main combatants, he was really big in casting this idea as in casting the foundational crisis and casting what he was trying to do with intuitionism as a revolution. And he was using kind of revolutionary language that mirrored what was happening in Russia at the time. And that's the other thing. A lot of what I talk about in this book took place before, during, and after World War I, immediately after World War I. And so everybody was in a war mentality anyway, and they used the war language metaphors anyway. And that's where the title came from, really, was The Great Math War, is a play on the term the Great War, because it sort of landed right in the middle of this.
Now, each side had its own version of what truth meant.
Right.
Who are the players? These people feel almost like generals if we're playing on the war metaphor here.
Right.
So how would you characterize their missions?
What Russell tried to do prior to World War I was to really work out the logical basis of mathematics, and he wrote one of the most important books in logic ever written, the Principia Mathematica, and it was hailed as a tremendous success, even though it didn't ultimately accomplish its goal. It didn't establish the logical foundations of mathematics. And so after World War I, there were two other mathematicians who led two other attempts to basically try to solve the foundations of math in two different ways. And so one was David Hilbert, and he developed formalism and metamathematics, which was an idea of like treating mathematics as a formal rule with games, a formal game with formal rules, where it didn't really matter what objects you were looking at in mathematics. It was really a question of what rules and how do you work out the solutions to the problems that you're asking. The way I think of this is the game of chess. And so in the book, I talk about how I have 3 separate chessboards in my house. When I play chess, I have an old plasticky set where, I play. But the point is that it doesn't matter what the set is or what the pieces are. You know the rules. You know how the pieces move. The pawn moves 1 space forward or 2 spaces on the first move, et cetera, et cetera. And so David Hilbert thought, math should be the same way. It should be a game of rules, and we simply figure out how to solve problems on that basis. And then he had his, sort of arch nemesis was a Dutch mathematician whose name was Bertus Brouwer, L.E.J. Brouwer, who he developed intuitionism as his approach to mathematics. And it was the idea of math as being a constructive process where you have kind of whole numbers And mathematics is simply the way that the brain goes about constructing things mentally. And it was a very different, very original approach. And people were very excited about it at the time. Remember, he was calling himself a revolutionary and calling his mathematics revolutionary. It tended to be a little bit unwieldy, and ultimately it fell out of fashion because, well, number one, he egregiously lost the great math war to Hilbert. But number two, he sort of gave up on his ideas himself. In fact, sadly, later in life, he basically said, I don't like mathematics. And that was the sad legacy. Now, if I could just say one last word about Brouwer, at the very end of my book, I talk about how I think his ideas are worthy of revisiting and worthy of digging up again for very specific neurological reasons, because I think that modern neuroscience is starting to show that some of his ideas about how we construct the world mathematically, how we see things, are turning out to be correct. And I talk a little bit about, at the end of the book, about this growing literature of other animals that could do math, chimpanzees and apes, even crows. So just a few years ago, some researchers in Germany discovered that crows can be taught to peck out recursive sequences, which recursion was something that was always thought to be solely an aspect of human intelligence, but crows can apparently learn to do it. Babies can reason. There was another study just a couple years ago that showed in Barcelona that showed that infants as young as a year old or, a year and a half old, they can form competing hypotheses and weigh between the competing hypotheses to come up with a conclusion. And that's extraordinary. Now, why is that? Why is it the case that, that all these different animals, crows and even Nemo, the anemone fish. Apparently, it turns out, researchers in Japan showed that anemone fish are able to recognize other anemone fish that are within their family group by counting the number of stripes on their body. And they do this very accurately. They do it very quickly. And so why is it that all these different animals have the ability to do math? I think that math is going to turn out to be a fundamental human primitive, something that goes way back in evolution, and it basically conferred on human populations and many other different species the survival advantage of being able to assess data, to weigh, make decisions based on data, to count, as Robert Frost said, counting winter dinners one a hill. The idea of, being a hunter and gatherer who can actually quantitatively assess, have I gathered enough food for the winter? That's a huge, huge survival advantage. So I think that all that is very compatible with Brouwer's worldview and his idea of coming up with mathematics as a way of assessing things based on simple counting.
Now, I'm curious. Hilbert's confidence was legendary, and his belief was that every problem could be solved with enough human ingenuity. So do you see the echoes of that same optimism in today's tech world with AI? I know, it's a little bit of a parallel here.
Yeah. No, absolutely. So that's a great question. I mean, I start out my book in the year 1900 in Paris in the summer, and the Paris Expo is going on. There are all these new futuristic things on display, cars, for instance. Most people have never even seen a car. The city is filled with cars that summer. And also at the Expo is the very second ever mathematical congress. The International Congress of Mathematicians is taking place that summer. And they held it because they thought that the Expo would be a draw that would attract more mathematicians. Hilbert gave one of his the most famous things he ever did was give this lecture in 1900, the 23 Problems lecture, where he talked about the future of mathematics. And he talked about it in a way just by simply laying out, here are 23 problems that we need to solve. And these were not easy problems. I mean, some of them had bedeviled mathematicians for centuries. I mean, Kepler's orange stacking problem was one example. So some of these problems had been around for many years. None of them were going to be easy to solve. And by laying them out, what he was doing was he was inviting people to kind of come and apply themselves, because, as you said, he very much believed that any problem could be solved given enough time and energy and patience and hard work, that you could do it. And in fact, what I call that in the book is, I call it exuberant solutionism, was his philosophy. He really did believe that we could solve any problem. And I think that this was really the birth of what we call futurism. Now, futurism wasn't actually born, so to speak, until a few years later. There was an Italian artist, Tomasino, who coined the word futurism in a newspaper article. But it was really Hilbert, I think, who sort of gave this flavor, this modern flavor of futurism, where we see the future as one of inevitable possibility, not hard possibility necessarily, but inevitable. And so, in 1900, as today, we had this sense that if we can conceive of the problem, if we can conceive of it, we can solve it. And so, I think it's also, I think it's a fallacy. I don't think that all problems are solvable. We know that, right? But also, I think that sometimes the implementation is way harder than we're allowing ourselves for. And so if you talk about something like curing cancer, ending all disease, people don't even stop at curing cancer. The kind of things that you hear today are, we're gonna cure all diseases in a decade, and people attribute that, AI is going to get us there. Well, that's what we're going to do. It's almost inconceivable. I will allow, in the universe of possibilities, that could possibly happen, but it's never going to happen. Honestly, some diseases, the hardest, our greatest successes are abysmal failures. We're just not able to, comprehend and understand. And, part of the problem when you start to get at your question with AI is, will we be able to have general intelligence AI such that we can go further than taking existing material, processing it, and then spitting out an answer based on that? Will we be able to have an AI that will actually invent new things and have those things be right? That's a big question. My own background in graduate school was in structural biology, and people sometimes talk today about how the protein folding problem has been solved. We can take the sequence of a protein and we can tell you what the three-dimensional structure is. And to a certain extent, that's true. And programs like DeepMind deserve a lot of credit for really going further than anyone had ever gone. But there's a major flaw. So programs like DeepMind are great if you give it a sequence and you say, what does the protein look like based on this sequence? If it can match that with existing structures that are out there, it does a really good job predicting it. But if you give it a sequence of a structure, a type of structure that's not solved, it doesn't do so well.
So you situate most of your ideas in the book on the upheaval of the early 20th century. Now, 2 world wars, fascism, and the Great Depression. Why was it important to tell the human side of the mathematical story?
Right. Well, to me, all stories are human stories. And I don't just try to tell the background of what's going on. And I think a lot of historians do this. A lot of people will sort of situate the story very much in what's going on at the times. But at the same time, the kind of things that you see that I consider to be flawed are sometimes writers will focus on their subject matter and everybody else is kind of window dressing. I mean, they're there, but they're sort of in the background. And I really like to, I mean, I think some of the minor characters are just as interesting, if not more interesting. And that's certainly the case in this book. I mean, Albert Einstein is a minor character in this book. He pops up several times and he plays very key roles at important points in moving this narrative forward. And nobody could argue. I mean, he's one of the most interesting people, of the 90s, bar none. But there are several other examples. I mean, I talk about Sofia Kovalesky, who's the first woman to get a PhD in mathematics, and her childhood. I talk about Emmy Noether and just the way in which the barriers that women of their generation faced in getting PhDs in mathematics and getting jobs in mathematics. I mean, Einstein considered her the greatest mathematician of her generation. And she went years working in unpaid positions at university. She finally got her first paid position in the 1920s, almost 2 decades after she had gotten her PhD. And this is, a lot of men in her generation, her cohort, had gone on and on and on up the rung, up the ladder. So I want to tell their stories. I think that getting to your question and looking at the very early stages of what would, emerge and ultimately become World War II and the Holocaust, those early stages involved the Nazi takeover of the German government and also the persecution of Jews in German academia. And it led to something called the Great Migration, where a great number of university professors fled Germany with their families, many of whom came to the United States and really sort of transformed all kinds of fields in the United States, not just mathematics, the social sciences, physics. And this was really a direct result of Nazi persecution. I mean, they came to power 1933, and that's kind of where my book ends, is this terrible dark period where they took over the universities and there was some resistance. I mean, I tell the story of James Franck, the famous physicist who was a professor. He was a colleague of David Hilbert's, and he stood up to the Nazis. He protested them, and an amazing story. And so, I think that story has to be told. I am not the first person to tell it by any stretch of the imagination. I think that it, should be told over and over again, because we have to really consider what we're doing even today if we start, looking at academic freedom and what are we doing to universities today.
Now, also with this, you write about the moral collapse of science during that time. Now, do you see similar risks today when we separate ethics from innovation?
Yeah, I mean, I think that it's important to think about, embrace, teach, and talk about ethics at every level of every profession. I don't know what the solution is, but the kind of things that happen today, for instance, the type of misinformation that you see online, that you see in social media, it's beyond anything that I've ever seen. It's not like these ideas are new. When people talk about vaccine denialism, vaccine conspiracy theories, when people talk about, I don't know, power lines cause cancer, these ideas have been around for a long, long time, but they have more force behind them now, it seems, than ever before. And they have platforms. People are, openly talking about these things, whereas even just a couple years ago, you couldn't be seen as being a conspiracy theorist. And now, people are empowered to do that. And what scares me is the idea that perfectly reasonable people will go along with it because they think that the writing is on the wall. Okay, now we don't believe in climate change anymore. And so I'm going to say the things that, that go along with that. And, you see this. I mean, I don't want to name names, but I saw a company kind of rebrand from their climate change roots into like a different different field just to sort of avoid that kind of scrutiny. And I mean, universities, I think are struggling with what do we do? Do we resist? Do we stand up? Do we go along? Ultimately, let me just say, ultimately, I am an idealist, and I think that's a position that's very compatible with an ethical approach. And so, but I want to say more about that. I mean, I think that idealism has always gotten a bad rap, at least in my lifetime, because people present idealism as being at one extreme end of a spectrum at which sits the other end, realism. And so you're almost an idiot to be an idealist in some ways, because who doesn't want to be a realist? You're just living in a fantasy world. But I don't see idealism like that. I don't think that the spectrum is from idealism to realism. I think you can be a realist idealist, if you would. I think that it's very possible. Those two things are very compatible. I mean, you can be a cynical idealist. That cynicism is a form of realism. So I think that, the issue is not that idealism sits at the opposite end of the spectrum in fantasy land from realism.
Now, one of the reoccurring ideas in the book is Ignoramus et Ignoramnibus, which is we do not know and we will not know. How do you personally interpret that phrase, especially in the book?
So that phrase comes from a guy named Émile de Bois-Reymond, who was a famous French philosopher and physiologist. He was actually an early neuroscientist, I guess you could consider. He discovered, I think, action potentials in neurons and the electrical basis of communication all over the body. And so he was also famous as a philosopher, and he came up with this philosophy that became known as triumphant pessimism. And it was this idea summarized by the phrase you just said, where, there are things we will not know, that we cannot know, the known unknowns and the unknown unknowns. And, his idea was that there were problems we would never solve. There was knowledge we will never obtain. And it was a very popular idea by the end of the 19th century when David Hilbert came and gave his speech in Paris in 1900. Really, the speech was a reaction against triumphant pessimism. And that's why I called Hilbert's philosophy exuberant solutionism, because it was the opposite of triumphant pessimism. Now, I think, so there are a couple things I want to say about it. One is the irony of Émile de Bois-Reymond is that one of the examples he used for his triumphant pessimism, things we would never understand, was, were the senses, the human senses. And he was an early neuroscientist, if you will. He was a physiologist, and he said it's too complicated. We will never understand how smell works, how taste works, how touch works. And of course, we have come a long way. Now, I'm not saying we perfectly understand, but we do have a very good sense today of how receptors on the tongue, in the nose, on the skin, how they sense, sometimes physical stimuli, sometimes chemical cues, scents and smells and tastes and molecules on our tongue. And those trigger, depolarizations that send signals to the brain that are integrated within our brain. And we understand it as sight, seeing, touch, and all that stuff. And so he couldn't have been more wrong. I mean, we really, really understand this stuff very well now. But in a sense, I think we need to embrace the way in which he was right, that there are some things that we cannot know, that we will not know. And there are probably some questions that we should abandon or some efforts that we should give up because of that, So does it make sense to spend a fortune trying to do something when we don't really have a chance of succeeding? And I would say no.
Now, you also you talk about neuroscience as well, and how the book shifts from 1900s to the dawn of modern day neuroscience. How did you actually decide to talk about that, and also some of the nonlinearities in mathematics as well?
Well, so it was really a conversation that I had with a friend of mine who, had his daughter was the same age as my daughter. And he told me about how he had a conversation with her, and which he basically said, okay, you're not good at math. I'm not good at math. You get it from me. It's genetically inherited. And it was a very dispiriting conversation, as you can imagine. And that really got me thinking. I mean, I didn't have the right way to sort of contradict him. I didn't understand the neuroscience enough, and so I started looking into it. And also, I mean, one of the other things that I researched in this book was eugenics, because the eugenics movement was very big in the same time period. I mean, it kind of exploded onto the scene prior to World War One. Then after World War One, it became really big. It was basically invented in Britain, developed in America, and brought to its evil, awful, heyday perfection in Germany. Then the idea of eugenics and sort of the genetic basis of things like mathematics, and so I was researching that. And that's when I happened upon this literature about neuroscience and animals doing math and things like that. And that's when I basically began to form the opinion that math is a human primitive. It's something that we all can do, that we're evolutionarily designed to do. Uh, and that, really I think the important thing today is to think about what does that mean in terms of, in terms of children, in terms of teaching kids math and early elementary education, because there's a sense in which a lot of what we learn, a lot of what we need to learn in mathematics happens at home prior to kindergarten. And so how do we best
Sure.
prepare kids for, mathematics? And these are some of the ideas that I'm exploring now, but it's fascinating. I mean, there's a lot of research and data into this, looking at, the kind of activities that people can do to set up a home numeracy environment, as they call it. And, as a parent in the last 20 years, I read to my kids. Every parent I knew read to their kids. We all read to our kids. We're all encouraged to read to children. And, but who, if anyone, does math with their kids? And if they do math with their kids, how do they do it? And so these are the kind of things that I'm thinking about now. And I think that part of what motivates me as a writer to write about math and write about history and try to make it interesting for everyone is to sort of inspire people to think about some of these ideas, even in, very, very, very vague ways.
If the I'll say the first great math war was today, what would that look like? Would it be AI, consciousness, or computation? We can't always have all of those three things to be the same. It's not going to be the same theme. Where are we heading now?
I think that we still have a long way to go in terms of our understanding of the human brain. We do have good imaging, but you look at all these fMRI studies that come out, they're resolution limited. I mean, we're talking about hundreds of neurons, thousands of neurons, whole discrete sections of the brain. There are other studies that look in a very definitive way at individual neurons even. And there are animal studies, and we could do optogenetic studies of the brain. But I think there's still a long way to go to really discover all the ways that the human mind works. And I would say, to a certain extent, also the animal mind, because we have a lot of similar physiologies to other animals. That's why animal models are effective. So there's that. I think that often a lot of what drives science is a specific need. So, we learned more about the immune system in the last 40 years than we knew or ever discovered in the last 400. And that was largely driven by the HIV/AIDS pandemic. And so, the amount of research, the amount of studies, we teased apart all these different immune cells, where they're born, what they do, what receptors they have. And I think the same is true for neuroscience. I mean, we're driven in a needs-based way. We want to understand autism. We want to understand Alzheimer's. We want to find ways of curing Alzheimer's, not just slowing it down. And so that drives a lot of the research. And so really what you're asking is kind of a much broader non-needs based question. And I think that those are some of the most interesting questions.
A lot of the computation that we have today and the models, I'm curious, as you were writing book, if we're looking at this, was there anything that you found to be very interesting when going through it or that surprised you?
Yeah. Well, so I developed a series of fallacies and paradoxes that I named. I basically developed by looking at the history. And so that was some of the most interesting stuff. I talk about the illusion of desperate deliberateness, which is the idea that very highly successful people often have, where they think that everything that happens to you is a direct result of your deliberate action, and how that's actually a fallacy. I talk about that in terms of Kurt Wittgenstein was the father of Ludwig Wittgenstein, the famous philosopher. And 4 of Ludwig's brothers had like terrible, terrible times because of Kurt's, business first notion, this idea of the illusion of desperate deliberateness. There's another thing I talk about, which is the fallacy of pure process data, where we look at data and we're chasing data. It's very similar to Goodhart's idea in economics, where when a measure becomes the goal, it ceases to be a good measure. And that's something that's, discussed in economic circles. Well, the fallacy of pure process data is a much more fundamentally psychological idea, that the data itself is something that we measure to think that we're succeeding. And so I talk about it in the context of the British Boer War in 1900, which was the largest war that Britain had fought in a century and the most costly, most destructive. And in order to win this war, they instituted a terrible policy called land clearance, where they were basically burning farms and turning families into refugees. The idea was to kind of burn the farms, and then the guerrillas who were fighting them would have no place to hide. But it created this massive refugee crisis where there were, tens of thousands of largely women and children who were suddenly homeless. And so they then implemented a policy of concentration camps. And so first concentration camps in the 20th century were run by British soldiers. And this was something where they did all of this because they were chasing numbers. They were saying, okay, we need to burn a certain number of farms per week. We need to put a certain number of farms out of business, out of commission.
So was there a favorite part of your book that you wanted to talk about right now?
One of the things that I really delighted in writing this book was the idea of infinity, and the idea that, I say at one point, that infinity has been around for a long time. And that's true. The ancient Greeks debated about, what infinity was and what it meant. We all take these classes in college or high school about Zeno and Zeno's paradoxes, and the arrow that never reaches the target, and the tortoise who beats you. Achilles never catches the tortoise in a foot race because he has to go half the distance and half the distance again and half the distance again, ad infinitum. And so we're never able to do that. And so the Greeks wrestled with infinity, and all through history after that, philosophers, poets, mathematicians, everybody sort of wrestled with infinity, but nobody really tackled it, conquered it, understood it until George Cantor in the 19th century when he invented set theory. And in doing so, he came up with this idea of denumerable and non-denumerable, big infinity and little infinity. And one thing I say in the book, I describe different ways of contemplating this. And so you can think of countable infinity, the small infinity, almost as a beach with an infinite number of grains of sand, right? And so you cast your eyes over this beach and you've got all these infinite grains of sand. It's an infinite beach. The uncountable infinity, the larger infinity, is where you think about not only the infinite grains of sand, but think about each individual piece of sand and all the different individual crystals of minerals in that sand and all the different facets and all the quantum states of all the particles and all the atoms in all the grains of sand. And you can go on and on and on. It's an infinite look at each infinite grain of sand. And that's how I describe as the difference between big and small infinity.
Is there one idea that you hope readers carry with them after closing The Great Math War? What would it be?
Well, I would say that it's not an idea so much as a person. Sofia Kovalesky, the Russian mathematician who wrote, very little. She died at a very young age, but she was the first woman to get a PhD in mathematics. She was the first woman in Europe to be a professor of math. She was the first woman to serve on an editorial board of a math journal. And she had an incredible life that, it reads like a Hollywood movie. She also was a good writer. She wrote an autobiography, which I read in translation in this, doing this research. It's amazing. And this is somebody, she learned mathematics from wallpaper. She's the only person in history to ever learn her subject from wallpaper. And it was because, her father was some famous Russian general. He retired when she was a girl, and they moved to a country house and they brought enough wallpaper. They fought to paper the whole house, but they were one roll short. And the old general got, furious, Boris, you forgot, you didn't bring enough wallpaper. Go back to St. Petersburg. And then he changed his mind. Well, let's just use something else in Sofia's room. She's the youngest. So they decided to paper the walls with his old college notebooks from his mathematics courses. And that's how she learned math, was looking at these stories. And so the idea that I wanted to say to your listeners, if there's anyone out there who is looking for an idea, who's looking for a subject, for a film, for a book, this is a great subject. She is very unknown, I think, in the United States. She may be, more famous in Russia, but she's basically forgotten. But she had an incredible life. So if you're out there, if you're thinking about, I would really like to write a story about, a famous mathematical figure, particularly a woman, there's your subject right there.
Jason, thank you so much for coming on the show. The story of the Great Math War reminds us that even the purest logic comes from human hearts, and that every equation in some way is a reflection of our search for meaning. And as always, history has a tendency to repeat itself. So until next time, stay curious and stay informed.